Normal force. When you have an object resting on a surface, the surface exerts a force. For example, I've got a box resting on the floor. What are the forces on the box? Well, we've got gravity pulling down, call that mg, and we've got the floor pushing up on it, preventing it from falling through the floor, and we call that the normal force, N. In this case, it's a very simple problem. The net force in the vertical direction, put a little y there, is mass times the acceleration in the vertical direction. And the net force is just going to be the normal force pulling up minus mg pulling down. The acceleration is 0 because it's at rest. So the normal force equals mg. That is, they're equal and opposite. Their magnitudes are equal, but we can see from the free body diagram that they're in opposite directions. Okay, let's try a problem. A 35 kilogram crate rests on a horizontal floor. And a 65 kilogram person is standing on the crate. Determine the normal force that the floor exerts on the crate. So we've got the crate and we've got the floor. Well, and then we've got also the person up here. A happy person with a crooked smile. So the forces on the crate. We've got, if we draw the free body diagram, all the forces are up and down. There's no horizontal forces. We've got gravity, but now we have to be specific. This is the gravity, the weight of the crate itself, mass of the crate times g. We've got the person standing on top of the crate, pushing down on the crate. That is mass of the person times g. And then we've got the normal force of the floor pushing up on the crate. That is normal, I'll say, from the floor. And we want to know that normal force from the floor. So if we look at the net force, again, they're only vertical forces, so I'll put a little y there, equals mass times acceleration in y. We've got normal force from the floor minus the ones pulling down, minus mass of the crate times g minus mass of the person times g equals the acceleration in this case is 0. So if I solve for the normal force, add those to both sides, equals mass of the crate plus mass of the person times g. And that is going to be 35 kilograms, the crate 35 kilograms, plus 65 kilograms times 10 meters per second squared. That's g. That's 90, 100. That would be 1,000 newtons. Okay, now determine the normal force that the crate exerts on the person. So if we do the free body diagram for the person, I'll just put a P there. We've got the force of, we've got the normal force from the crate pushing up, and we've got just the weight of the person, mass of the person times g pulling down. And the acceleration again is 0. So the net force in y equals mass times acceleration in y. We've got normal force from the crate minus mass of the person times g equals the acceleration is 0, so that side's 0. So the normal force from the crate is just the mass of the person times g, which is 65 kilograms times 10 meters per second squared, which is 650 newtons. So, Let's look at the next one. A 95 kilogram person stands on a scale inside an elevator. What is the apparent weight when the elevator is accelerating upward with an acceleration of 1.8 meters per second squared, moving upward with a constant speed, and accelerating downward with a constant acceleration of 1.3 meters per second squared? Okay. Here we have the person in the elevator. There's a normal force pushing up. There's gravity pulling down. And in this case, we have an acceleration upward. Notice I didn't put the acceleration on the free body diagram because it isn't a force. Only forces go on the free body diagram. The weight of the person doesn't change. The weight of the person is constant. But the normal force, the amount of force being pushed, that's pushing him up, that can change. And that is equal to the apparent weight or the scale reading as he's going upward. So if I say the net force in y equals m times acceleration in y, I have normal force minus mg equals ma. So the normal force equals ma plus mg. So that's going to be mass times acceleration plus g. Mass is 95 kilograms times, I'm using, let's see, 1.8 meters per second squared, plus, I'm just going to use 10 for g, meters per second squared. So that'll be 95 kilograms times 11.8 meters per second. And that is 1121 newtons. Now, in this problem, we're only given 3 significant figures, so we should probably round it off to 1120 newtons. Okay? In the next problem, it's the same exact problem, except now the acceleration is 0. When the acceleration is 0, even if you're moving, it would be at a constant velocity, the net force is going to be 0. So I can use this same equation, n equals m times a plus g, except now the acceleration is 0, so it's just 95 kilograms times 0 plus 10 meters per second squared, and that's going to be 950 newtons. Just the same as it would be if the elevator wasn't moving at all. And finally, in the third part, we have the acceleration is negative 1.3 meters per second squared. So because the elevator is accelerating downward, that might mean the elevator is going downward and going faster and faster, or going upward and going slower and slower. Either way, the acceleration's downward, and it doesn't matter which one it is. So now our normal force is going to be m times a plus g, which is, I'll write it down here, 95 kilograms times negative 1.3 meters per second squared plus 10 meters per second squared. And that is 827 newtons. So when you're accelerating upward, the apparent weight, the scale reading, the normal force is larger than your actual weight. When you're constant speed, the normal force is the same as your actual weight, and when you're accelerating downward, it's less than your actual weight. So friction. Friction is mu times n. Mu is the coefficient of static friction or the coefficient of kinetic friction. Okay? There are different numbers that you use depending on whether the two surfaces are sliding past each other or not moving relative to each other. In the case of static friction, if you have an object that's at rest relative to another surface, we call that static friction, and it's mu static times n. Actually, I should write here, instead of equals, I should say less than or equal to. For example, if I have an object, a block, resting on a table, it's going to have gravity and normal force. If I push on it with 1 Newton, and friction is preventing it from moving, this would be static friction, it's not moving, then the pushing force and the static friction are the same. If I push on it with 2 Newtons and it's still not moving, the friction force would be now 2 Newtons. The friction force can't be larger than the pushing force, otherwise it would be accelerating in the opposite direction, which doesn't make sense. So sometimes the static friction is less than mu times n. Mu times n is the largest it can be. The equation looks almost the same for kinetic friction, except that we have subscripts k, and we don't have the less than or equal to. Mu k and mu s are just numbers that we look up in a table. They depend on how sticky the two surfaces are. N is the normal force. That depends on how much the two surfaces are being pushed together. A couple things about mu. The coefficient of static friction is always greater than the coefficient of kinetic friction. Maybe you've experienced this. If you're trying to move a big piece of furniture across the room, it might be really tough to get it going, but once it's going, it's easier to keep it going at a constant speed. That's because the coefficient of friction is less when the object's moving. Also, mu is a unitless number. If we write F sub k equals mu sub k times n, I'll divide by n. Mu sub k equals F sub k, that's a k, over n. F is friction, that is measured in newtons. N is normal force, that's measured in newtons. So the units here would be newtons over newtons. They cancel. It's just a ratio of two forces. So let's try a couple problems. Problem 1. A cup of coffee is sitting on a table in an airplane that's flying at a constant altitude and at a constant velocity. The coefficient of static friction between the cup and the table is 0.3. Remember, that's a unitless number. Suddenly the plane accelerates, its altitude remaining constant. What's the maximum acceleration that the plane can have without the cup sliding backwards on the table? So the cup is resting on the table. The forces on the cup, we have gravity, mg, and normal force, n. We also have friction actually pulling the cup with the airplane. Before the airplane starts accelerating, it's in equilibrium, but then the plane accelerates, and it's the static friction that's actually pulling it, say, to the right. And the acceleration, remember, I'm not putting that on the free body diagram. The acceleration would be to the right also. So the net force the net force in the vertical direction, let's do that in red. Net force in y is going to be mass times acceleration in y. That'll be normal force minus mg equals 0 because the acceleration's 0. So at mg, the normal force equals mg. That'll be useful because normal force is important for friction. So if we look at the net force in x, that equals m times the acceleration in x. The only force in the x direction is F. That equals m a sub x. And the friction force, this is static friction, is, remember the friction force, I'll do a different color. F is less than or equal to mu static times the normal force. We want to know the largest acceleration that we can have without it slipping. For that, we would need the largest friction force. The largest friction force is when this is an equal sign. F equals mu times n. So I'm going to say mu static times n equals m a sub x. And the normal force is equal to mg. So I can say mu static mg equals m a sub x. I'm going to divide by m, those cancel. So now my the acceleration is mu static times g. And I know both of those things. Mu static is 0.3, g is 10 meters per second squared. So the acceleration, the maximum acceleration without slipping, would be 3 meters per second squared. Here's another one. Let's try this one. It's almost the same thing. A bucket sitting on the bed of a pickup truck that's driving at a constant velocity. Suddenly, the truck accelerates at 1.5 meters per second squared. What's the minimum coefficient of static friction that would prevent the bucket from sliding backwards? Almost the same thing, but now we're finding the kinetic friction. So we've got friction, normal force, gravity. Like in the last problem, the acceleration up and down is 0, so the normal force equals mg. And the friction, we want the maximum friction possible, so this is going to be mu static times the normal force, which equals mu static times mg. Now the net force is just going to be the net force, we're just looking in the horizontal direction, equals ma. So on this side, the net force is that friction force, mu static times mg equals ma. And the m's cancel, we divide through by m. Now I'm trying to solve for mu static. So mu static is going to be a over g. A is 1.5 meters per second. Meters per second squared over g is 10 meters per second squared. So mu static is going to be 0.15. Remember, it's a unitless number.